So next we'll do question 8.8. 5 kilograms of air initially at 600 kilopascals and 410 degrees Celsius is expanded adiabatically in a piston cylinder device until the pressure is 100 kilopascals. Assuming it produces 550 kilojoules of displacement work, what is the entropy change during this process? And is this process realistic? Assume constant air properties evaluated at 300 Kelvin. Okay, so we're going to look at this process and see if it makes sense. So we can already kind of see a little bit maybe what we're getting at when we talk about a process being realistic is, well, if it satisfies the first law of thermodynamics, a real process has to also satisfy the second law of thermodynamics. Now, what does the second law of thermodynamics tell us is that if there's no heat rejection, the only thing that can really happen is for the entropy to increase, or if it's a perfectly reversible process, then stay the same. But what we're getting at is that for an adiabatic process, meaning no heat transfer, meaning no heat rejection, meaning no decrease in entropy. So if we do the math here and we see that there's a decrease in entropy, we know that it doesn't add up and that this process is not realistic. But if we do the math and we see that the entropy is positive, then we'll see that, okay, well, it is a realistic process. At least it obeys the second law. And of course, if the entropy change were to be zero, well, it's not it's not realistic in the sense that nothing is truly isentropic in real life. But in theory, it doesn't outright violate the second law. Anyways, so let's see what the change in entropy, if it's positive or if it's negative. So to do this, we're going to use the relationship, let me find it, which you'll have seen in class is delta S, being the change in entropy for an ideal gas, by the way, is Cp times the natural log of T2 over T1, so that's the temperature at state 2 over the temperature at state 1, minus R, the gas constant, times the natural log of P2 over P1, pressure in the second state over pressure in the first state. So of all this information that's given, what do we know? Well, we know the pressure 1 and we know the pressure 2 and we know the temperature 1, but we don't know the temperature 2. So how can we find the temperature 2? Because we obviously have to find what that is before we can make use of this equation. Well, we're told some additional information in the question. We're told that the work done on the system is done by the system is 550 kilojoules. And we know from the first law of thermodynamics that for an ideal gas in a piston cylinder, work equals mCv times the change in temperature. So, and we expect this to be a positive value. We know it's a positive value, actually. We expect the work to be a positive value because the piston is doing work, it's expanding, it's doing work. So we're going to use positive 550 in this. So thing is, we're not trying to find the work, we're trying to use this to find T2. It's just that we have enough information to find T2 using this equation. So if we rearrange it slightly, we can get T2 equals T1 minus work over the mass of the system, or the fluid in the system, times CV. And again, CV, CP, and R are all coming straight from the one of the first pages of the property tables, and this is all for air. So let's actually do it now. T2 equals, well, T1 we're told is 410 degrees Celsius. So we have to put that into Kelvin. So plus 273. So 410 plus 273 is 683. So that's T1. minus work, which we're told is 550 kilojoules, divided by, we're told the mass of the system is 5 kilograms, and CV for air is 0.718 kilojoules per kilogram Kelvin. And if we calculate this, we will get a value of 529.8 Kelvin, which is a lower temperature than what we started with. And again, we kind of expect that because we just underwent an expansion. The pressure goes down, the temperature goes down. So this is all consistent so far. Anyways, this is the second temperature that we have. So now we're going to plug all this information into the first equation I wrote up here for delta S. And we're going to see if delta S is positive, negative, zero, or what the story is with that. Just be really careful with the temperature ratio. Again, since it's a ratio, we are using Kelvin, because if you use Celsius, you'll get wrong results. So delta S equals Cp, which for air is 1.005, ln of T2 over T1, so 529.8 over 683, minus R, which again for air is 0.287, P2 over P1, so 100 over 600, or since it's just a fraction, just 1 over 6 if you want. And if you calculate this, we'll get a value of 0.259 kilojoules per kilogram Kelvin. In other words, the entropy is increasing. This is perfectly realistic because, like we said earlier at the very beginning, we just want to make sure that the entropy isn't negative. And it's not negative, so this process is definitely realistic.